Hello and welcome to this video. My name is Sonko Julian Paul, member of Cs-26-2, and our project is about federated dermatology screening with vision language models and skincare recommendations in Uganda. So the background motivation for this project is we start with the figure around here. 1.9 billion people are affected globally by skin diseases. Here in Uganda, we have less than, or approximately less than, 25 dermatologists for a population of 45 million Ugandans, and we have severe violations of SDG 3 and 10, which address health and AI disparities. So what has been done in the field? In the field has deep learning models. It has very advanced multimodal vision language models such as CLIP, Lava, and Florence 2. We also have other specialized models such as Skin GPT-4, Skin, and make frameworks that bring AI to clinical dermatology. Then we also have GANs such as the Albano Pix2Pix that generate synthetic skin images to address data scarcity. However, what the market doesn't have are these gaps over here. We have dataset bias, in which most AI models are trained on lighter skin tones. We have no privacy preserving solutions, in which people always have to send their pictures to the server for inference before a result is sent back, and then your picture remains on a server. Then existing tools just send classification labels without a proper treatment plan, as well as large models being too heavy for deployment on a mobile phone. So what's the problem that we state from here? The problem is stated in three ways. The first is the privacy barrier, which I explained. A privacy preserving solution would allow you to get inference on your device, or allow you not to send your image and maybe send extracted features. You have deployment feasibility, where models are usually too large to sit on a mobile phone or a resource constrained device. And then you also have no treatment pathway. Aside from getting a clinical diagnosis, they do not, most of them do not provide a proper treatment pathway. So what do we do as a group? Our main objective is to develop a privacy preserving federated AI platform that provides real-time dermatological screening and evidence-based skincare recommendations, which are specifically tailored for Uganda's low-resource clinical environment. And in this, we look at four major things under the objective, which are privacy, accuracy, efficiency, and guidance. We keep the images private, so features are extracted from the mobile phone, and inference can also be done on the mobile phone. Accuracy, in which we try to get the things right. Efficiency, where we have legislation that we have the smallest possible models deployed for the job. And finally, guidance, in which after that diagnosis is made, we have treatment planned, we have symptoms from a knowledge graph and a graph attention network, and so on and so forth.
My name is Arnold Okello, and I'm motivated into the rest of our presentation. So our specific objections, first is the robust diagnostic model, where we shall benchmark of 8 black vision models to develop an physics encoder plus an ML classification pipeline optimized for 8 inferences. Then we have knowledge distillation, where we shall compose that LVM into a lightweight mobile small student that can be deployed on Android via REST API. Then we shall also carry out federated feature learning, where we shall have distributed clients sharing feature level updates, not raw images, to a central gated server. And then we shall go through all this in our methodology. Then we have graph augmented treatment guidance, where we build an knowledge graph where the 82 diseases are our nodes. Then 968 ages will be our relationships. Then we shall use a GAT plus an LLM to generate explainable KG validated recommendations for explanations so that the users can understand. Next, this is the pipeline we shall use. First, we shall go through federated feature learning. Then we shall train our teacher LVM. Then knowledge distillation, where this is where we compress our teacher LVM into a lightweight model that can be deployed on the smaller Android devices by REST API. Then we shall have inference and breadcrumb, GAT, KG, and reasoning. Then LLM synthesis, where we have structured treatment output, which is basically explanation for to the user why the model has chosen that. Then these are the different datasets and tools we used. Knowledge graph, VML models use CLIP, Florence, of course, we chose the best. Then I want to focus more on the federated clients here, where we have different federated clients that were used to send the weights to the main server for aggregation. Here we have now our methodology, where we have the training phase. In the training phase, we shall have our main server here. So the main server here will go through what we call federated feature learning. In this case here, we shall have distributed clients, like I mentioned earlier on. These are the different clients. They will send their weights to the main server. So the main server will create an average, then send back to the different clients. Then the main model, the CLIP model, the LVM, was trained based off the damned dataset. Then after this is the whole teacher LVM. So it's compressed into a smaller student LVM. This is the process of knowledge distillation. So in this stage here, this is now deployed on the different smart devices. So when the client inputs an image, we shall produce two things: one, a probability vector, and a feature heat map. The probability vector will be used by the GAT and the knowledge graph to generate context that will be used by the LLM to generate an explanation of what treatment recommendations can be used and which disease has been identified in this case. Then the feature heat map will tell the user what the model used to which parts of the image the model used to come up with this conclusion, to come up with this vector. And yeah, basically that is basically what happens. Yeah, thank you.
My name is Senko Ushan. I'm going to go through the models and their results. So the 8 models, the CLIP model performed the best with 72% accuracy and a macro F1 score of 0.72, and then a 47 percentage point gap between over its own zero-shot performance. So on top of having the smallest encoder footprint of all of them, which was approximately 600 MBs, which is very important of course, for deployment. So it's also the results from the federated learning, where when we ran a federated fed average against all the 5 clients, which notably had a non-IID, a non-implement independent and something distributed data, the fed average actually collapsed because there's only one class that had an overlap. So when we switched to fed procs plus soft pseudo labels, that's how we ended up with this accuracy of 71.76 as compared to the baseline of 72. And then also, of course, the bandwidth that we achieved was crucial, was notable, because since we only exchanged the head, only the MLP head is exchanged rather than the full model. You only use 277 MBs rather than using 60 GB if you had sent the full model. The student model that we used to train from the clip, which achieved a 62% accuracy as compared to the 72 from the clip model. Moving to the results from the knowledge graph. The knowledge graph had 82 disease nodes, 391 symptom nodes, 313 treatments, and then the 968 relationship edges between them. So that GAT correctly classified, performed based on the neoplastic classifications. I want to note that metabolic had at 0%, but there were only 3 metabolic classes. So it couldn't create a training set for them. So that's why we have 0% there. Then for the infectious, autoimmune, 40%, and neoplastic as well performed best. And when you added it with a 5.3 mini LLM, the disease is covered to the 25% accuracy. That increased to 62% when you add the knowledge graph. And then the miss rate also greatly reduces from 75% to 38%. When you look at all these results, the meanings of all these results, the frozen encoders, of course, contrastive pre-training produces linearly separable embeddings, where frozen encoder plus MLP avoids catastrophic forgetting. Here, this is when you choose to fine-tune the clip model, you risk overwriting the generalizations that you get from this. So when you use a frozen encoder, you maintain that structure, which reduces the GPU demands and then actually outperforms full fine-tuning in this resource-constrained setup. For federated resilience, soft pseudo labels plus the fed procs, I mentioned this, prevented the 64-point accuracy collapse seen with the vanilla fed average because of the non-IID clients. I mentioned this. The distillation trade-off, where the 9.8-point gap here is concentrated in the fine-grained inflammatory cases, where Clip's vision language pre-training model provides semantic inductive bias unavailable to the mobile version that was deployed. For neurosymbolic grounding, the KG raised treatment coverage by 37%. The benefit concentrated in metabolic, parasitic, and genetic conditions whose regimens lie outside Phi3's, the LLM's default high-frequency parametric knowledge. Basically, when we added the knowledge graph, it supplied validated clinical facts at inference time, which helped to fill in a gap from the LLM. The skin tone equity gap, training on damnets, and then predominantly lighter Fitzpatrick types, limits the generalization. So the TMC Ugandan dataset was inaccessible, and integrating the SNDDI datasets is the primary next step. So this is under the future works. It was one of the limitations that we had because the DAMNet dataset has lighter skin tones, and TMCG dataset that we needed we couldn't access it. So we can't claim that our accuracy, the accuracy figures generalize very, very well for the Ugandan population. But this is, mentioned in our feature works later on. And then deployment context, the API-based survey, 38-millisecond server latency, which outperforms on device TF Lite on compatibility.
Hello, my name is Cesar Mike. I'm going to take you through the rest of the presentation. So I'm going to start with the deployment architecture, and here we have a hybrid development architecture. We'll start with the device side, whereby everything related to the image happens locally. So the camera captures the skin lesion, and the image is preprocessed by the student model, which runs the inference. Then immediately after classification, we apply a GradCam to the same student model to generate a heat map that highlights which regions of the image influence the prediction. Importantly, to note, the raw images never leave the device. So only the prediction result, the top three classes prediction, the confidence scores for the top three classes, and the heat map are sent to the server. Then on the server side is where we find the heavier components, like the graph attention network, the knowledge graph, the large language model, and the structured diagnostic that comes from all that. So the graph attention network operates over a large medical knowledge graph and containing like DAMNet categories and skin to retrieve clinically relevant information related to the predicted condition. This structured knowledge is then passed to the large language model, which is Phi3B, which synthesizes into a human readable diagnostic narrative. And then the final report is then returned to the device and displayed alongside the prediction and heat map. This gives the clinical team or the person rendering the image to both the visual representation and also a text that rationalizes how we reached here. Important thing note, the images never leave the device. Then we have the limitations. Here, although our system achieves strong performance, there are several limitations. For example, the training and experimentation time was constrained by Google Colab and GPU quotas. This restricted both the training duration and the extensive hyperparameter optimization. Also, we have limited computation resources, likely disadvantaged by the larger vision models, and this prevented completely fair comparison of the full capabilities because we had less resources. Then another limitation was the Qwen 2.5 virtual language model and did not really support GradCam visualization in our selected configuration. So this reduced our ability to visually exploit model decisions compared to other architectures. Also, access restrictions prevented evaluation of some models that would have liked to use like TMCG dataset, which also limited validation directly within the intended Ugandan clinical environment, because the Ugandan datasets were harder to get. Some hospitals didn't have the exact data that we needed, and others you had to go through a long process and we didn't really have access to them. So in our future works, we plan to fine-tune and evaluate the platform using locally collected Uganda clinical data in order to improve real-world accuracy and generalization. We also aim to develop a structured dermatology dataset that combines the images with important metadata such as the diagnosis, the skin type, the lesion location, the age group, that sort of thing. And we also intend to use semi-automated annotation approaches like the segment anything model or the YOLO V8 to accelerate lesion segmentation while also maintaining our clinical oversight. Also, finally, I think we plan to establish collaborations with Ugandan hospitals, clinics, and health centers to collect a representative local dermatology dataset as one of our goals. Yeah, we want to curate it and then come up with the dataset. Then also, these future improvements basically would move the system closer to a more practical clinical deployment. In conclusion, this research successfully demonstrated a privacy-preserving scalable AI approach for dermatology screening, and our best performing model was the CLIP VIT, Vision Transformer L14 with a frozen encoder and MLP classifier, which had an accuracy of 72.09% and an F1 score of 0.72. Then also we employed federated feature learning together with soft pseudo labeling and fed procs, and doing this, we were able to maintain a stable performance across distributed clients while reducing communication requirements by about 217 times compared to the full model federated learning. Then we also did noise distillation, which allowed us to compress the teacher model to a MobileNet V3 small student model with only 1.54 million parameters, making the deployment practical while also maintaining the competitive performance. Then, also in addition, combining the knowledge graph with a 5.3 LLM increased treatment coverage from 25.4% to 62.4%, demonstrating a measurable improvement in recommendation quality. Overall, this work provides a scalable blueprint for privacy preserving and equitable AI diagnostics in low-resource African healthcare settings, such as contributing to the SDG 3 and SDG 10. Yeah, thank you.